Hello, everyone. Welcome to today's discussion where we'll be discussing low-cost and open source tools, next steps for science and policy. Really excited to have you all here. I'm Allison Parker. I'm a senior program associate with the Science and Technology Innovation Program at the Wilson Center. For those not aware, the Wilson Center is the official memorial to President Woodrow Wilson, and it's also a think tank and nonpartisan policy forum for tackling global issues through independent research and open dialogue. So we're really excited to play that role today, hosting this conversation that is exploring the opportunities and challenges and potential of low-cost and open source tools for science. It's really clear to me by the participation in this event, the interest and the fact that we're all really excited by what we see emerging as to how people around the world are using low-cost and open source tools for science. We're seeing things like low-cost air quality sensors, allowing community members to collect their own data on local air quality. We're seeing things like microprocessors and desktop 3D printers, allowing scientists around the world to make their own customized tools for original research and share those tools with others. We're doing that to build an infrastructure for shared scientific progress. And more recently, we observed how grassroots communities really mobilized to contribute to shortages of personal protective equipment and other medical supplies in response to the COVID-19 pandemic. And of course, there are a huge number of other examples in a variety of disciplines and communities and industries, from microscopy and imaging to health, medicine, conservation, open source satellites, robotics, et cetera, et cetera. And we'll hear about some of those examples today. But it's clear that these tools are more than just objects, and because we can see that they have the potential to really change how we are approaching science in allowing us to align with open science and open innovation more broadly. These tools are really expanding the way we think about science by broadening participation in science and helping us align the use of science for society priorities and public priorities, including through contributing to the increased impact of citizen science and community science approaches. And again, we're seeing these in a variety of scientific disciplines, and we're seeing growing libraries of tools and developing a real shared public resource available for replicable and rigorous use. And also we're seeing huge contributions to participatory STEM education, among many other things. So we'll hear a lot more about the potential and possible futures for low cost and open tools throughout the discussion today. And in particular, we'll focus in today on open source tools for science or open source hardware, given that it has unique value in enabling anyone to study, modify, distribute, make, and sell tools for science. I'm just going to share real quick a few resources that are recent work that have begun to demonstrate the potential here for low cost and open source tools for science, starting with the initiative think tank, which is from, again, the Science and Technology Innovation Program at the Wilson Center. And we're thinking about how the things of science, again, the physical tools that generate data or contribute to scientific processes, are accelerating and broadening science through this initiative that builds on open science and open innovation approaches. And we're really grateful to the Sloan Foundation for funding these impactful questions. I'll point to some recent work, including this report that looks at some case studies in low cost and open source tools for science, including one from a panelist that you'll hear from later. This report, Building Blocks for Better Science, by myself and Alexandra Novak, to look at, or we look at the boundaries of scientific, the creation and use. Beyond that, with collaborators and representatives of communities like the Gathering for Open Science Hardware and the Open Source Hardware did a virtual workshop with experts from key messages for the audiences. Really pleased to see a collection of curated insights by the Journal of Open Hardware on media and upcoming policy make the case for why hardware needs policy. And then finally, as the COVID-19 crisis has unfolded around us, we worked with the Engelberg Center for Law and Policy at NYU and a roundtable of representatives, including one of our panelists today, that were directly involved in the response to medical supply shortages during initial stages of the COVID-19 pandemic in the US. And so we're also really pleased to launch today a report that documents this roundtable and the of open source hardware community, the sizes from those discussions, insights for future crisis. Check out those. Explore possible futures of low-cost science, including how increasing government attention to these open agendas can complement growing community capacity. And we'll look at where we are today as we move into a new presidential administration. And we can think about what are the possible futures for low-cost and open tools for science that will enable increased impact on science and society. So we'll approach this conversation today as one input to a series of conversations and a start to the look of possibilities within low-cost and open source hardware for science. And we're interested in bringing together a wide variety of disciplines and communities, from environmental to space policy, STEM education, health, again, many more, to address how common challenges and opportunities can help us define a broader umbrella. So throughout the panel discussion and the closing remarks, please feel free to send any questions or comments to stip@wilsoncenter.org. And particularly those that you'd like addressed by our panelists or any that we in STIP can follow up on after the event today. So with that, I will introduce Anna Persick, who is the Acting Chief of Science Policy and Partnerships section at the Division of Science Policy and Capacity Building at the UNESCO headquarters in Paris. Anna focuses on strengthening the science policy interface and the promotion of science, technology, and innovation in the implementation of the United Nations 2030 Agenda for Sustainable Development and the Sustainable Development Goals. So we'll hear from her actually in a pre-recorded message due to the time difference about UNESCO recommendations on open science. Thanks, Anna.
So thank you for the invitation. I'm very happy to be part of this conversation. Unfortunately, the time zone is a bit of a difficult for me, but I am sure that you will have a good discussion live as well. And if there are any additional questions for me, I'm very happy to respond also by email or by any other means. So I'm very pleased to be able to present to you today the work that UNESCO has been doing on building a global consensus on open science, in particular in the context of developing a UNESCO recommendation on open science. Why the need for open science? Why the need to open science more to scientists themselves, but also to the society more broadly? We live in a time that we can really see, particularly from the current pandemic, how important it is to have timely and accessible access to scientific data, publication, and information. It is also extremely important to have scientific collaborations and sharing of information at all levels between the different disciplines, between the different regions and countries, between also, as I said, scientists and society. And also, it is extremely important to nurture and to enhance a science policy society dialogue that is really building on trust and that can advance science also so that it really benefits society as much as possible. So this need for open science, we have known for it for a while, but I think the current pandemics, the current situation has made that even more visible for many of us. So from the UNESCO's perspective, open science really is this movement to transform and democratize the entire scientific process. As I said, it allows scientific information, data, and outputs to be more widely accessible and more reliably harnessed with the active engagement of different stakeholders. And even more importantly for UNESCO, we do see open science as a real game changer to bridge the science technology innovation gaps between and within countries, and also to fulfill the human right to science. So we know that in the Declaration on Human Science, we do have this right to enjoy the benefits of science, and it is extremely important to promote this right. And we believe that open science really is an important tool to reach that goal. And also within the UN system, we see open science as an accelerator for the implementation and achievement of the United Nations Sustainable Development Goals. Having said that, it is also important to say that there is huge potential in open science in terms of really opening the scientific process at the different elements and the different parts of the scientific process. But we have to work on it together, and we have to work on it in a very responsible way, because open science also can have potentially unintended consequences in maybe even increasing this gap between those who have and those who have not, including when it comes to, reliable access to IT technologies or other means which are actually very important in terms of open science. So this international solidarity and international collaboration in terms of promotion of open science is going to be incredibly important if the open science really is to reach its potential as a tool to bridge the gap in science technology innovation across the world and truly benefit society and all its members. Now, an issue that we have with open science for the moment is that currently there is no internationally agreed standard on what open science is, what the values are, what the norms are. And we have a pretty fragmented scientific and policy environment. So in that context, actually, as I said, the global understanding of the meaning, opportunities, and challenges of open science is still missing. And that is the reason why UNESCO's member states, 193 member states, tasked the organization to develop an international standard setting instrument on open science in the form of what we call a UNESCO recommendation on open science. So in this context, we have started in 2019 leading this consultative process towards the recommendation, which hopefully will be submitted to UNESCO's General Conference in November this year for adoption in November this year. So just quickly on what the UNESCO recommendation is, it is a legal document, instrument, in which the General Conference of UNESCO formulates principles and norms for the international regulation of a particular question, and then invites member states to take legislative and other steps to actually implement those norms and apply the principles and norms within their respective territories. So it does emanate from our organization's supreme governing body, and these recommendations are really intended to influence the development of national laws and practices. So even if it's not as legally binding as a convention would be, it still has pretty important weight in terms of how it influences the development of national laws and practices. As I said, what was extremely important for this recommendation is like the process of developing the recommendation is almost as important as the recommendation itself. And then really what's going to be critical is how do we implement the recommendation? How do we make sure that in every country and in every setting, the recommendation makes sense and it actually does move things forward in terms of transitioning to open science. And to be able to develop a recommendation that is acceptable for all, the idea really was to have a broad range of consultations, as inclusive as possible, be it in terms of inputs received from different stakeholders, such as young scientists, citizen science academies, libraries, open access platforms, publishers, UN system, indigenous peoples. We've had consultations with many of these stakeholders. And then we also had regional consultations, and the regions are those of UNESCO. So we had one for Africa, Europe and North America, Arab states, Asian Pacific, Latin America, Caribbean, and Eastern Europe. And we also had, throughout last year, we had this online survey, which was held for almost 6 months last year. We received almost 2,900 inputs from 133 countries. So we got a lot of inputs that were guiding us in developing this draft, the first draft text of the recommendation, which is now in the hands of our member states, actually. This first draft, as I said, was developed in collaboration with our Open Science Advisory Committee. And this committee is really, it's 30 people coming from different countries, different backgrounds, extremely important in really gathering the feedbacks from different communities and from different regions. So the Open Science Advisory Committee helped us in UNESCO to develop this first draft with the inputs from the members themselves, the UNESCO Open Science partners, through these consultations, multi-stakeholder consultations, regional consultations, the online survey, and also through discussions with the different member states. We've produced the first draft, sent it out to the member states in September last year. And it was open for comments and inputs until the end of last year. And right now we are actually in the process of analyzing all these comments on the first draft and trying to incorporate all these comments into a second draft, which is going to be sent to our member states at the end of March, and then we'll go into the intergovernmental negotiation process. So just at this stage, what we have in the Open Science recommendation, it might be interesting for your meeting in particular. So of course, there is the preamble, aim and objectives of the recommendation, definition of open science, the core values and guiding principles, areas of action, and how do we monitor the recommendation. I'm not going to go into too much of a detail into the text because it is still available, and please do have a look at it. But I think it's important to maybe just highlight a few things in terms of the aim of the recommendation. I think what came out very clearly from the different inputs is that the recommendation is intended to really provide this international framework for open science policy and practices that is cognizant of the regional differences in open science perspectives, and it recognizes the specific challenges of scientists and different open science actors, particularly in developing countries, and that it contributes to reducing the digital, technological, and knowledge divides existing between and within countries. So the recommendation really is a tool to work towards reducing this gap, as I was saying in the beginning. As for the definition of open science, the definition as it stands now, it really refers to this umbrella concept that combines various movements and practices which aim to make scientific knowledge, methods, data, and evidence available and accessible for everyone, increase scientific collaboration, sharing of information, and then open the process of scientific knowledge creation and circulation to societal actors beyond the traditional scientific community. So it's really kind of acts on these three points. Although we now, in some of the comments, we see that we can even go further in defining open science in this global framework. Another important point in the recommendation, of course, that the scientific outputs should be as open as possible and only as closed as necessary. Of course, mindful of issues relating to security, privacy, respect for subject of study, and some additional restrictions that are going to be very carefully determined, because it is also true that opening data, opening science comes with a lot of responsibility. And it is also important that any opening of data, of course, contributes to the quality of science and contributes to the dissemination of science and building the trust in science, and not vice versa. So again, we are living in a time that has shown all the pros and cons and risks related. So it is important that the key objective of open science always stays the supreme quality of the information that is coming into the world and that is shared with everybody. In terms of core values, we have quality, integrity, inclusiveness, equity, fairness, collective benefit, and diversity. Again, the comments that we are receiving, there is a lot of other things that will probably be added further on. In the guiding principles, transparency, equal opportunities, sustainability, flexibility, collaboration, respect, responsibility. So all of these guiding principles are very important. And it is important to have a place, an instrument that actually really clearly delineates what these guiding principles are and what the core values for open science practices and policies are. In terms of areas of action, we have 7 key areas: promoting a common understanding of open science, developing and enabling policy environment for open science, investing in open science infrastructures and services, investing in capacity building for open science, transforming scientific culture and aligning incentives for open science, promoting innovative approaches at different stages of the scientific process, and promoting international cooperation on open science. And we've seen from the comments received that people are, both member states and partners, stakeholders, are generally happy with these areas of actions as areas of priority for a fair and just transition to open science. Now, before I close, I would like to also point to a few issues in the recommendations that are of particular relevance to your meeting today. One of the ways in which open science is also defined in the text so far is as a complex of different elements, which include open data, open access, open engagement with the societal actors, open educational resources, open science infrastructures, open evaluation, openness to diversity of knowledge. We've had lots of contributions from different stakeholders and also from different member states with this idea of the importance of open science to also be open and build these linkages with other knowledge systems, including openness to all scholarly knowledge and inquiry and indigenous knowledge systems. Another element which is also important is the open source software and open hardware, and I believe this is really part of your discussion today. I have here a little definition, if I can say, that we currently have in the text now, which can be useful also for your discussion, and we would very much appreciate some feedback on what is still missing here or what is there that maybe shouldn't be there. But I think what was very important while drafting the recommendation, and particularly this part, is to be cognizant of the fact that both open software and hardware, in the context of both open software and hardware, a community-driven process for contribution, attribution, and governance should be in place to enable reuse, improve sustainability, and reduce unnecessary duplication efforts. So I believe this is also going to be part of your discussions during the meeting, and we would very much appreciate feedback on this also to enrich our recommendation in this particular field. Just to close with a couple of points on what the next steps are in the process. It is that, as I said, the member states and different actors have provided their comments on the first draft. This draft is now being revised based on the comments received, again, with the help of our advisory committee. We have a first meeting actually on Monday to look into the different comments that have arrived. And then, as I said, member states will start their negotiations. They will meet in a special committee meeting, hopefully in May. We are hoping for them to be able to meet face to face. Not sure if that's going to happen. If not, we're going to be creative as we were so far to negotiate the text of the recommendation. If needed, there is going to be another set of recommendations. Other actors will also be invited as observers. So we will be reaching out also to some of you who have already contributed to the recommendation to continue being a part of the process. And then, as I said, the final text will be presented in November this year, 2021, to the 41st session of the General Conference, which is supposed to consider it and then adopt it if the member states so agree. The real work will only start then, because really it is an ambitious document, and I think member states really want it to stay like that, as an ambitious document. So the implementation of open science, knowing that there is no one way or one action plan for all, knowing that there is going to be some considerable adjustments depending on where the countries are coming from, where the actors are coming from. It's going to be very challenging in terms of implementation, but also a very good exercise for the scientific community and also all the open science actors together. So we will definitely be counting on your help throughout the process, and particularly once we start implementing the recommendation on the national and regional and international levels. So thank you very much. I will stop here, and I wish you a very good meeting.
Excellent. Thank you, Anna, for that. I'll now introduce Ann Bowser, my colleague in the Science and Technology Innovation Program and Director of Innovation at the Wilson Center, who will in turn introduce our panelists and moderate the discussion. Ann.
Thanks, Allison. I really wish that Anna could have been here. I thought that was a fabulous keynote, but it's 10 p.m. in Paris, and she's had an entire day worth of parsing comments from member states, as she described in her keynote. But reflecting on what she said, something jumped out at me, which was the process of developing the recommendation is as important as the recommendation itself. One, I think that's really valuable in terms of lessons to share with all of us, many of whom are working on building open science agendas in the United States from various angles. But I'm also really happy that she included that, because as soon as the camera went off, she said, well, the real challenge is going to be implementing the open science recommendation. And we talked for a bit about what that might look like, and two things came out that were relevant to the panel. First, she mentioned the need to compile success stories, both on practical and policy levels of open science projects that worked. And then she also talked about the need to understand accelerators and barriers and how to deal with each, as she's trying to encourage all of the member states and everybody else in UNESCO's broad network to move this important piece of work forward. And in terms of the panel, we have three people here today that are going to speak to both of those points. First off, we have Megan Mccarthy. Megan is a program lead for 3D printing and biovisualization in the Office of Cyber Infrastructure and Computational Biology at the National Institute of Allergy and Infectious Diseases, part of the US National Institutes of Health. She also oversees NIAID's services for 3D modeling and printing and research and development in virtual and augmented reality for scientific and biomedical visualization. Dr. McCarthy is an advocate for open source software and design sharing and contributes to working groups dedicated to the improvement of 3D data standards and initiatives promoting women and minorities in STEM. We also have Dr. Gerald Stinger Guala. Stinger is a program scientist on long-term detail from USGS in the Earth Science Division at NASA. He wears several hats in the Earth Science Data Systems program, including oversight of the Multi-Mission Algorithm and Analysis Platform, which is a cloud-based joint project between the European Space Agency and NASA. He is also the Earth Science Point of Contact for Citizen Science and coordinates the Citizen Science for Earth Systems program, which sponsors numerous citizen science projects that leverage, enhance, or expand NASA Earth science observation systems. Lastly, we have Zach Manchester. Zach is an assistant professor of robotics at Carnegie Mellon University, founder of the KickSat project, and member of the Breakthrough Starshot Advisory Committee. He received a NASA Early Career Faculty Award in 2018 and has led 3 satellite missions. His research interests include motion planning, control, and numerical optimization, and his passion is expanding access to space by developing open source technologies for building smarter and cheaper spacecraft. The format of this panel is quick interventions by the 3 panelists, followed by a moderated discussion. I have a couple of questions in mind, but we'd really love to hear from all of you. So please send your questions to stip@wilsoncenter.org. That's STIP for the Science and Technology Innovation Program at wilsoncenter.org. Megan, please tell us about your work.
Great, thank you. Thank you so much for having me here. I'm really excited about this. As you gave my introduction there with all of my hierarchy of affiliations within NIAID, open source has been a real passion of mine for a long time. We founded the NIH 3D Print Exchange in 2014, which is an open portal. It's community driven, it's free for people to go and share and create models related to 3D printable models related to bioscience and medicine. We launched that in 2014, and last March, at the outset of the pandemic, as we saw such this amazing response from the open hardware and 3D printing community, we partnered with the FDA, the Veterans Health Care Administration, and America Makes to create an initiative where at NIAID, we extended our platform to help curate all of these 3D printable PPE and devices that were being shared across the web. They were tested by engineers from the VHA. We had the FDA on board to inform helping people navigate all of those regulations and capital G guidance and lowercase g guidance. And America Meeks was our liaison to industry that helped build a bridge between organizations in need of supplies and manufacturers with 3D printing and additive manufacturing capabilities, with the idea that this technology enables a stopgap to help support shortages in the supply chain, especially as all of our other manufacturers with traditional manufacturing methods sort of retool their production lines. And then we also coordinated with community organizations like Nation of Makers and Open Source Medical Supplies, who are doing really amazing things to harness the energy of those communities. So yeah, my work, I'm really interested in helping to make this kind of data, adhere to FAIR principles of being findable, accessible, interoperable, reusable, all of that good stuff. And that includes improving data standards for things like 3D file formats and what kind of metadata we're collecting and how do we make that interoperable, particularly across the web. And to maximize utilization of resources that come from government funding that would support the open source community to share their work. And I think that kind of open sharing is really essential to innovation and collaboration. So I'll leave it there.
Thank you, Megan. Before we move on to the next panelist, I'm sure that you were incredibly busy during 2020 and 2021. But for a minute, take us back to 2014. What was it like to get this started at NIH?
Oh, so that was actually really exciting. Our work with 3D modeling stems from mostly molecular modeling and structural biology. And we wanted, so our website, it's a repository that people can share from. And I think we almost called it at the outset, like Thingiverse for science. But we've also created web tools that allow people to upload their own data that will generate 3D printable file formats. So kind of eliminating that that barrier, going from like atomic coordinates of a protein structure to something that's printable. And in building out the 3D print exchange, we said, well, you know, we're at NIH, let's make this broader across, you know, hosting medical models, anatomical models, and then custom hardware, particularly with a focus on laboratory equipment. So, and that was great. We actually launched that at the White House Maker Faire in 2014, and through the Obama administration spent a good amount of our effort coordinating with people across different government agencies through the White House Office of Science and Technology Policy.
Thanks for sharing. Speaking of history, Stinger, you've held numerous leadership positions in biodiversity and big data over the years. What are you working on now? There you go.
There we go. Yeah. So what am I working on now? Well, I run the Citizen Science for Earth Systems project at NASA, the program, and we're just about to announce a whole new crop of new projects that we're funding. I'm really excited about them, but I can't say a word because we haven't announced them yet, unfortunately. Sorry about that. But we do have an older crop that were funded in 2016, and those included actually kind of competing projects, which have now collaborated, looking at air quality. And one of them's using the purple air filters that we all know about in this realm. And the other one is using a optical, I think they're called A-mods that they've developed. And this is aerosol mass and optical depth. So they not only measure PM 2.5, but they also measure the optical depth. Now the purple airs are $200 to $300. These A-mods are about $1,000, but they're making some big inroads on how we measure air quality. There's another sensor, open source sensor project that we funded that uses Arduino, and they're getting very accurate soil moisture readings. That's based at JPL. It's Dr. Das. And these sensors cost about $17. So that's kind of amazing that they can turn that out. All of our CSES projects, the Citizen Science for Earth Systems program, all of our projects are required to follow open science rules. All of the software is open source, all the hardware is open science compatible. They're releasing all of the data. That's all required in the solicitation. Some other things that I do at NASA, I'm also the deputy lead, which means I have to do a lot of the stuff for the Google Global Partnership. with earth science. And so that factors into the whole open science and getting things available to the public. We do a lot of work with Google Earth Engine in that realm. And one of the things that we find in NASA in big data is we make all our data available. We have a series of these data centers called DACs around the country, and they make petabytes and petabytes of data available. We were just trying to figure out how to move a 5 petabyte data set to Google Earth Engine this morning so that they could use it as well as us. So it's weird in that the access problem for developing countries and under-resourced institutions and things, it's not about getting the data, it's about being able to download it and use it. It's too big. So that brings me to the multi-mission algorithm and analysis platform, which is going to release in March. Another thing I would love to talk about, but version 1 doesn't release till March. We've been working 2 years on it, and it is our showpiece for open science. Everything we did, all of the requirements are built around open science principles. And it's a giant analysis platform in the cloud. So we're bringing the data to the processing. And you can spin up a supercomputer in the cloud and do your processing. And you can do it on demand. We're trying to figure out right now how much we're going to let the public do that because it's expensive. But the public will have access to the system. It'll be fully public. You'll be able to go there and browse the data. And it uses open source principles and collaborative programming. All the Jupyter notebooks, all the code, everything's available, and you can collaboratively program. I have some of the staff have sat down with me, and I'm not a good programmer, and they can make fun of me right there in the program and help fix things. It's really a powerful thing. And the initial use case for it is above ground biomass. So we have one user right now, and he's from Gabon, which has the tallest mangroves in the world, and he can pull the data and do biomass estimates for those mangroves across Gabon on a regular recurring basis. So that's probably most of what I do at NASA that is relative to what we're doing here.
Thanks for sharing. And you already brought up 2 themes that I'll return to in the group discussion, one being the relationship between low cost and open source hardware and other areas of open science, and the second being this accessibility issue, namely, what does it take to actually get these devices used? But before we go there, I've got a little bit of a hard hitter for you. We were talking while preparing for this panel about all of the different, let's just say, air quality sensors out there. And you mentioned that you had, after Roses, a number of competing projects that have now collaborated. I think there's a major tension between encouraging different researchers and different communities to build their own devices, and then also not just having a million mousetraps out there, but kind of getting that collaboration and that convergence. Do you have any advice based on the lessons that you learned about how to navigate that?
You know, I would love to take credit for the collaboration, but I didn't do it. They came to me and said, hey, would it be okay if we shared our sensors? And I wrote back like, absolutely, it'd be okay. They had some challenges. They had some challenges related to COVID, where one of them, they were teaching classes that they had to get together to actually have hands-on with the sensors. And, that wasn't going to happen in COVID. So the other PI called and said, hey, we could borrow your sensors and just deploy them with some of our already deployed situations. And it worked out great. Getting people to collaborate, I think that the open source, open hardware paradigm is absolutely essential, because then you don't have licensing issues and, you know, all that kind of stuff to deal with. The funding agencies can encourage that. And I think in earth science data at NASA, you know, I've been in a lot of organizations. This is my 4th government agency I've been in. And I've worked on big data in all of them. And NASA is far and away the most obsessive about open science principles. So, you know, this is the way we work at NASA, and we encourage this kind of stuff. I think that's kind of key to the whole thing. And the other piece is you don't want to force collaborations where they might not be appropriate. You have to kind of let a grassroots need present itself and then encourage it. Does that answer your question?
Yeah, those are some great insights, and especially that last one, I think, coming from the funder perspective. But before we get to the group discussion, I'd love to hear from Zach. I'm completely fascinated by your work because of today's theme, but also the Wilson Center is starting our work in space. So let me know and let everybody know what you're working on.
Yeah, so I guess my sort of whole foray into the open hardware thing started about 10 years ago when I was a grad student and wanted to fly some satellites, and ended up as a starving grad student Kickstarter funding my space mission. It was, I think, you know, it was the first crowdfunded, or not, I shouldn't say crowdfunded, but definitely Kickstarter funded, you know, modern era of crowdfunding space mission. And one of my goals with the whole thing was, you know, growing up as a space nerd and always loving this stuff, we always think of putting things in space as the domain of national governments and militaries and big defense contractors. But there's really been this massive broadening of participation in the last 10 years or so with the proliferation of smaller and smaller satellites. So, you know, now instead of $100 million or more to put something in orbit, it can be done for $100,000 or even less. So it's become sort of the price of a car to get your own satellite in space. And in the last 10 years, a ton of universities have done it first. And now there's a bunch of startups doing it. But one of the things that I found trying to do this is that, you know, there's still this situation where there's a bunch of companies that will sell you satellite stuff in the hundreds of thousands of dollars range, even for these small, low-cost satellites. And if you're a university team, or now there's even been a couple of high school teams launching these small satellites called CubeSats that are about 1 kilogram, about this big. You're kind of on your own. If you can't afford the, you know, $500,000 widget from the company, you're on your own building this stuff from scratch, which can be done with kind of hobbyist electronics and Arduino kind of stuff and all the sensors we know from smartphones that have proliferated in the last few years. But it takes a certain amount of expertise and skill, and really, at the end of the day, trial and error and learning hard lessons by doing it a few times, right? And we've, in my lab, we've certainly had plenty of those. We're still having them. We just launched some satellites on Sunday that are, you know, on orbit now, and we're working the kinks out. So there's all these things that you just pick up as you go and learn. And one of the things that we've tried to do is, over the last several years of flying a bunch of these things, we've taken all that we've learned and all that we've built and distilled it down into a whole bunch of open hardware designs for all the avionics you need, basically everything you need to build one of these small satellites. So it's been radiation tested, it's been flown in space, it's been, you know, run through everything. And we've, you know, incorporated all those lessons learned, and we've tried to make it easy to get going with, easy to build, easy to program. You can program the boards in Python, which everybody knows now, right? This is the first language everybody's learning in school. And the whole thing you can put together for a few $100s. So we've done some hackathons with these things at schools in a few places, and we've tried to kind of get them out there to other universities and get more people spun up using them. And that's sort of our big thing right now. The project's called PyCubed. You can Google us. It's PY cubed spelled out. And yeah, that's what we're trying to do. We're trying to make it easier and cheaper for scientists, schools, you know, whoever wants to build their own satellites.
Well, congrats on the Sunday launch, first of all.
Thanks.
Also, you mentioned a lot of a very crowded space, and Stinger was talking about seeing some organic cooperation emerging. Do you see that in your area as well?
Yeah, I think one of the things there is that part of how this all got started, this whole small satellite thing that we've seen just explode in the last few years, is that there was an open standard that was defined in the early 2000s for these CubeSats. So it's 10 by 10 by 10 centimeters, and there's you can get the ICD online, you could download it. There's a PDF with all the drawings, and you can build your own that meets the spec. And if it meets the spec, you can go launch it. So that alone, I think, almost more than anything else, has been driving this whole thing. Because you know what to do, you can go get the specification. It's open, it's downloadable. So that's been sort of a focal point for a lot of the collaboration and innovation that's happened in the small satellite community over the last couple of decades. There are, I think, in the space realm, some unique constraints that make it harder. We have things like ITAR and export regulations and things that do make it a bit harder to collaborate, especially internationally. Yeah, I think being open about it and open sourcing everything, especially in the academic realm where we try to publish everything, and helps a lot, and has definitely led to us working with other people at other universities and that sort of thing. Yeah.
Great, thanks for sharing. So for the full panel, for the first question, I'm actually going to take something that came in from the audience. It starts with an observation that there are so many great low-cost, open-source citizen science initiatives across the world. How can we avoid reinventing the wheel in all of these distributed efforts? And Stinger and I started talking about a bit that direction, but then also, is there a central repository of projects, hardware, and design as part two? I saw Megan perk up, so I'd love to hear her take this first. And then as you three are thinking about these, also consider how do they relate to each other? So if there is one or more central repositories of projects, hardware, designs, does that stop us from reinventing the wheel? Megan?
All right, thanks. So it's interesting, when you're talking about not reinventing the wheel and not duplicating efforts, I think is really important for everyone, for us to look at where is there a need and what is the niche and where can you fit in. And we saw this a little bit. This is a little bit different than like open repositories and establishing those, but one example would be, say, like during the pandemic, everyone was sharing files of face shields, and a lot of them, even what we were getting on our site, a lot of them were kind of the same STL. The Prusa face shield was amazing, so everyone wanted to use that, but it was kind of all over the place. And I think thinking about like where people are going to bring, instead of think about like what you're putting out there and where you're bringing novelty. So I think like it's not enough to just share something, but actually to iterate on it. And one of the things that we really want to see is documentation and helping people, the file is one thing, but if you are going to say in the case of 3D printing, or even just with open software in general, like, documentation is a huge problem. So I think it's really key to think about that need, and where, each of us can make the biggest impact. I think where open science comes in relation to these repositories is building application programming APIs, application programming interfaces, which will make these interoperable so that data from one source can be pulled into another and they can be found across the web. And that's where those kind of data standards are really important. So like one example of not duplicating efforts, America Makes is building a model repository that's intended to be like, it's an extension of what we did with COVID 3D Trust, but like vetted designs that a manufacturer can go to and say, here's a problem, whether it's a pandemic and we need, face shields or face masks. It could be a wildfire. It could be, I don't know, some kind of disaster where there's a supply shortage and people can go and find that. And they're going to be using our site and others to pull that in and consolidate it so that people can find what they're looking for. So rather than people having to search like the whole NIH 3D print exchange or, all of these different sites, that's where they're bringing value in taking things in you know, not duplicating the entries, but actually helping people get to what they need through APIs to those repositories. And I think that's what's really important, is not just getting the data out there, but making ways that it is accessible. So, and I think having better standards is going to be a really important part of that process.
So just a quick follow-up, and I love that everybody on this panel is talking about fair or findable, accessible, interoperable, and reusable, in addition to open. In the world that you work in, how far advanced are those standards?
Not very far. In the 3D printing community, the most widely used format is an STL file, which was the format that came out in the 80s. Although I mean, just because it's from the 80s doesn't mean it's bad and old. But so like JPEG is an old format. But anyways, STL doesn't include any metadata with it, aside from, it's just the geometry. So if I am to share a file with Zach and Stinger, you know, Zach downloads it from me, he shared it with Stinger. All Stinger knows is the name of the file, you know, and what it looks like. He doesn't know, he doesn't have any instructions on how to print it. He doesn't know who it came from or how it's licensed. And now Stinger is someone who appreciates open data and science, and that, you know, may want to, you know, would be interested in going and tracking that down. But this idea of having like a provenance and ensuring integrity of the data, that's one of those things. And in the 3D printing community, licensing and attribution are a really big issue. And tackling licensing, not just from you know, people actually being, you know, paying attention to the license, and what it's the kind of use it's indicating, but also understanding the differences between copyright and patent, which is really big in hardware. So it's those kind of things that we need to help figure out. And I'm not really one for digital rights management on software, but how do you make things clear and transparent, but then also encourage the design and development community to use those standards and include that information, but then also the end users to go and look for it and respect it and build upon that appropriately.
Yes, Stinger, Zach, any responses or other thoughts on? Yep.
Yeah, I just wanted to amplify something Megan said about documentation. Coming from sort of the business end of all this in a working lab, where we, you know, sometimes know what we're doing. For us, it's always a matter of, is it easier? It's often the case that it's easier for us to redo it from scratch ourselves and know what we're doing than it is to get someone else's code or design to work. Because of poor documentation. It's almost more important than the work itself, I would say. And it's at least as important, if not more. And it's why often these things sink or swim, I think, is documentation and how easy it is to get up and running. And like I said, yeah, I can't tell you how many times we've just started from scratch and rewritten something ourselves or just redesigned something from scratch ourselves because the open thing that's available on GitHub or whatever, we couldn't figure out how it worked. We couldn't understand the code. We couldn't read the comments. There was no documentation. And to actually know what was going on, we had to just start from scratch ourselves. So absolutely 100% behind that sentiment. And I don't know how you culturally sort of get that into the community more. It's really hard, but it's so important.
Well, I think there is a way to get it into the community, and I've been interested in the last few years about how that's been developing. 5 years ago, we had a big conference, NatureServe and USGS, and we were looking at biodiversity data and a lot of citizen science data we were looking at and how powerful that was. And what we found was that there were these big repositories like GBIF that had the Global Biodiversity Information Facility, and they're sort of an aggregator of all the information. And then there were thousands of these little citizen science projects where they were collecting stink bugs, or they were collecting air potatoes, or name the species they were out there getting at. And I really had to stand up in front of a couple hundred people and say, just stop that, because if you're not collaborating with a repository, your science, you're getting good buy-in from the community, and that's valuable. But the science relevance of what you're doing is enormously reduced if you're not working with a repository. And the effect of working with larger aggregators and repositories is that your data, those issues in your data of not being well documented, the issues of not having the right metadata, the issues of not having the right format, those stand out. They are glaringly obvious the minute that you combine your data with other data. And as Megan said, the APIs and standards are absolutely essential. But having been in this business a long time, I can tell you that everyone has their own interpretation of most standards. If you look at, pick a data standard, and you will see wildly differing ways that that's implemented. So the way that those become really useful and workable for, like, Zachary wanting to build something, is that you have community norms that develop within those standards. And I think that's important. And these repositories force that.
And I just want to add to say that, with this idea of, how do you enforce it, is we're actually building, so NIH 3D Print Exchange, our next evolution of it is NIH 3D, and we're in the process of that. And the information architecture to the repository is completely different. It gives me heart palpitations just thinking about this process, at least in the data migration. But I think what's important is figuring out the requirements. And I think that's one way in which you can help avoid duplication of, well, not necessarily maybe avoid duplication of efforts. That's more about really taking a long, hard look at, is there a need for this, or am I doing it because it's something that we want to do? But it all ties together: requirements gathering and documentation and the standards, and exactly like what Stinger said, is building that community around it. But how do you rally people, especially in the open source innovation space, where it's really exciting and fast moving, and look, we made this thing, like, let's get it out there, and get people to kind of take a step back. And that's in particular with COVID 3D Trust, was the VHA said, we're not going to print this and review your face mask until you add all this additional documentation, which was one way to kind of wrangle that effort. But it's those sitting back and thinking about what are the requirements are really important. And I hate, because I sounds just like project management developer speak, but it is really important.
I guess I'll chime in.
Yeah, I think the other.
So I was just going to add.
I think the other force in the community. Oh, sorry. Go ahead, Zachary.
Latency.
It says you're muted on mine.
Let's do Zach, then Stinger.
All right. So yeah, I was going to add to that whole thing about metadata and attribution. There's something else there too that is missing from my perspective, that we've tried to do a bit with our stuff on the hardware side, is I can post design files and build instructions, but it doesn't get at why it is the way it is or how it really works. So one of the things we've done with the PyCubed thing is post this long form document on design decisions and try to document our design process. and explain to end users why the thing looks the way it does and why that thing's over there and connected the way it is, and why you shouldn't sort of try something else. This kind of stuff, like we try to document part selection and like the iterative process of testing and all the design decisions that went into this thing, and that whole history, which is not an easy thing to do. There's no standard ways of doing this. We have it like in a GitHub wiki and in a series of documents, because it's the sort of thing where like if me from 5 years ago went and looked at this, I'd be like, why'd they do it that way? And I would have thought I knew better and did it a different way. But it's like this hard one, these lessons of actually going out and doing stuff, right, and breaking it in a bunch of ways, and then you figure it out and you tweak it. That stuff just totally gets lost, and it's not in the hardware, right? And it's not in the design files. It's where is it? If it doesn't get recorded. So that's another thing that I'd be really interested in hearing people's thoughts on how to get that like design iteration process and like the knowledge behind the thing, right, or behind the design files out there somehow and documented.
I feel like we could do an entire different event on that, and maybe we will one day. But Stinger, I wanted to hear what you had to say really quickly, and then I'd like to go back to something that you said on infrastructure.
Yeah, so I just wanted to point out the other trend I'm seeing in the community, in the citizen science community, is that 5 years ago it was all about everyone building their own app, their own mobile app, things like that. And now there's so many good ones out there that have solved standardization problems, a lot of usability problems, that it really, unless you're doing something really, really strange, there are platforms out there that can be modified, and then you have something that's instantly compatible, and that's making a big difference. I'm seeing that happening in the community.
Thanks for that insight. And I do agree that that speaks to the maturity of citizen science, that there are these sort of reusable or configurable platforms that are becoming infrastructures that can support a wide range of initiatives. And you brought up another infrastructure, which is GBIF, which for people in the audience who might not be aware is a big biodiversity infrastructure that is funded by a range of governments as well as foundations and others. And I'm creating that touch point because we got a really good audience question that touches on aspects of funding as well as infrastructure. Are federal agencies or foundations stepping forward to fund the cloud-based hosting needs of real-time environmental sensor IoT platforms designed for public data sharing? In other words, how do we maintain the low-cost aspect of open access environmental IoT as the cost of hosting those data streams grows? And in regard to cost and hosting and infrastructure, I would also point out that there is significant cost to maintaining the communities themselves, including through community management and participation and moderation, which we've already touched on a bit. So who would like to respond to that question?
I can take a quick crack at it. So I know that through the programs that I'm associated with at NASA, we are funding participation in those public portals, which requires something. There are lots of NSF funds and NIH funds and other funds going into these large collaborative portals. But I think it's hit or miss. I don't think there's a concerted effort across government to fund these kinds of portals. But certainly NSF, Division of Biological Infrastructure, funds a lot of efforts in this area. And NASA's, anyone who funds these grants is going to fund participation in these larger portals, thereby supporting those portals, because it's like I was saying, you need to be part of that community to really be relevant scientifically. So it's kind of a forced situation.
Thanks for tackling that. Megan or Zach, would you like to come in or hold off? I see smiling faces and no one is unmuting. Okay. Well, we have a couple minutes left in the panel, and I'm going to close with a question that I was actually most excited to ask you all anyway. Throughout the course of this conversation, we've heard reference to lots of open science and open innovation approaches, low cost and open source hardware, the topic of today, but also open data, open source software, citizen science, even crowdfunding. And then Anna had a lot more up on her slide. How do you all think that open source hardware fits into this larger open science and open innovation ecosystem? Maybe Zach would like to start.
Sure, yeah. I think as an academic, for me, it's all about reproducibility. And we've all heard in a bunch of fields in the last several years about these crises of reproducibility. I mean, if I go publish a paper that relies on, so at this point, right, in computer science, for example, if I publish a paper with an algorithm and I have benchmark results and plots in the paper, I cannot get away with publishing that paper without having the code online for someone else to run to verify that the algorithm works, right? And I think a bunch of the hardware stuff is exactly the same way. If we're not open sourcing the hardware designs behind the results in the published literature, we can't reproduce the stuff. And it's just absolutely antithetical to the mission of academia. I think we have to have it, for that reason, if nothing else.
So it goes back to the core values of science. Megan?
Yeah, so I would definitely second that with regard to reproducibility. And one of the great things about open hardware is that it allows you, in research, and I come from a biochemistry background, or my PhD is in neuroscience. But, when I think back to had I had access to open hardware, the experiments that I could have done or ways that I could have done it maybe more efficiently, like, is really exciting to me, rather than some of the stuff that I had MacGyvered together with, whatever duct tape and, beakers and stuff that I had that was, nothing critical, but just that kind of everyday thing that if you can share that's really important. And people are using open hardware methods to make experiments faster and better and get advance that time to discovery. So it's not enough to just tell people what you do. You have to show your work. So like Zach said, if you want someone to be able to reproduce it, you have to put it out there, and documentation is very important. So it's all part of that process. But yeah, I think that's where it really brings a lot of value in that sharing.
Thank you, Megan. Stinger, last thoughts for the panel?
Yeah, I think in the government context, it's all about value. All of these programs, we get hundreds of proposals coming in, and they will want to do, they want to build their own hardware. And if we can fund a piece of hardware once, and then everyone else just uses that and does something better the next time, that's what we want to do. It looks, to keep rebuilding, reinventing the wheel, it's pretty irresponsible fiscally. So, that's the line in government. And we do try to stick to that. It's clear.
Well, that is a compelling argument. Thank you very much to all three of you. I wish we could talk about metadata for another 15 minutes. But I'm going to, at this point, turn over to Shannon Dose-Megan to close out today's event. Shannon is an environmental health advocate, community science champion, and enthusiastic about the potential for open systems and technology to support the creation of more just and equitable futures. Shannon is currently a Shuttleworth Foundation Fellow with the Open Environmental Data Project, co-founder of Public Lab, an executive director from 2010 to 2020, and serves on the boards of Code for Science and Society, the Gathering for Open Science Hardware, and the Journal of Open Hardware. She is previous chair of both the US EPA National Advisory Council on Environmental Policy and Technology, which some of you may know as NACEPT, and also the Citizen Science Association, or CSA. Shannon, thank you very much for joining us.
Thank you so much for having me, and thanks for the really great panel and discussion today. I think especially the last question is going to play a lot into what I share in closing remarks this afternoon. But generally, it's really exciting to see how many people are engaged and interested in this field. So to build on Anne's introduction, my dive into open hardware stems to over a decade ago. This was a time when the concept of open hardware was still relatively new or even unknown to many, but some of the underlying philosophy, driving down costs, creating shareable tools, building community, were present in a tool called the Bucket Air Monitor, modeled after the EPA Summa canister, and used by people around the world to collect air samples from the refinery they live next to. With this foundation for my work, and also recognizing technology is not a silver bullet, I've spent about the last 10 years figuring out ways to better connect people to using science and open hardware as tools to ask and answer questions that are of priority to their communities. Generally, this period from about 2009 to 2011 was really an important moment during which the foundation of open hardware was laid. So in 2009, there was an instrumental event called the Grounding for Open Source Hardware. In 2010, we saw the Open Source Hardware Association, or OSHA, be established. And then in 2011, the European Center for Nuclear Research, or CERN as it's most commonly called, launched their open hardware license. Between 2010 and 11, communities such as the one I'm involved in, Public Lab and Safecast, were established. And this is when really began creating and applying open hardware and the communities that surround open hardware to support people faced with disasters such as the BP oil spill and the Fukushima nuclear power plant meltdown. In 2015 and 16, a group of researchers, practitioners, passionate about the potential for open hardware as a tool across scientific practices, from physics to biology to citizen or community science and environmental monitoring, came together under the banner of the Gathering for Open Science Hardware, or what we refer to it as GOSH, to start building bridges between our work and to think about the broader infrastructural needs of the open science hardware community. One of the main ways we initially did this was through organizing global events, which people from over 40 countries have attended. And we danced around the globe, from Geneva to Santiago to Shenzhen, to try to bring these events to different places. And at the same time, we've seen regional communities such as GOSH Latin America and Africa Open Science Hardware emerge. Community members are connecting with each other through residency programs to solve complex scientific challenges with cross-disciplinary approaches, and they're hosting topical events such as open hardware in academia. Basically, the growth of this field has skyrocketed. Fast forward to 2017, where over 100 people from the GOSH community came together during the global gathering in Santiago, Chile, to produce a roadmap with the goal of making open hardware for science ubiquitous by 2025. Three key categories of recommendations emerged. The first is learn, so that we can identify and change the structures and processes that affect wider production and adoption of open science hardware. And we can do this by setting a collaborative research agenda, increasing knowledge about open hardware licensing, and better understanding how to monitor and evaluate open hardware projects. The second is support, so that we can create sustainability for open science hardware. And we do this by ensuring institutional support and funding. We connect documentation infrastructure, which we heard a lot of our panelists talk about, and we provide mutual support for each other. And then we grow the community so that we can increase support and mentorship for new members. We advocate for open science hardware within established institutions and ensure that it is supported by policy. And we facilitate a wider distribution of open science hardware. Some of the successes we've seen over the last several years reflect these recommendations. And to just highlight a couple, there's a growing number of companies that are sustaining themselves on open source hardware. To name a few: Opentrons, Open Acoustic Devices, Open BCI, Open EFIS, and so on. The Journal of Open Hardware and Hardware X have ensured a place in academic publishing for open hardware. Between them, there are now more than 100 publications. And CERN Open Hardware License 2.0 was released, which highlights the continuing commitment that a major research facility like CERN has in this field. Since the earlier days, we have been focusing on connecting, expanding, growing the role and place of open science hardware, but still pushing for even just the integration of open into the broader landscape of scientific inquiry and DIY making practices. Right now, though, there is a big opportunity. With a new US administration in place that's highlighting the importance of scientific integrity and decision-making, coupled with a commitment from administration leaders to ensure that science agendas connect to societal priorities, we need to create a policy culture that matches our drive for technology innovation and considers usability in tandem with open. That is why open hardware needs key policy attention now. Starting with the GOSH roadmap as the foundation and stemming from a fall 2020 workshop, over the last 2 months, 17 contributing authors wrote a series of recommendations that emphasize open hardware in the new science policy agenda as an immense opportunity to advance research and innovation infrastructure while also addressing other critical priorities. So each article, and thus the slides that I'm going to show you, or Allison's going to show you, have a series of very rich and considered recommendations. I encourage you to take the time to read all the articles, as I cannot do content to the justice in the limited amount of time that I have. And I'll highlight one recommendation from each slide, but these slides will also be available on the event website afterwards for you to read. So first, with COVID-19 as the global backdrop, contributors highlighted, the two contributors on the slide highlighted the ability to leverage the culture of innovation and rapid creativity found in many open hardware and maker communities. This was demonstrated in the rapid response of open hardware communities in creating and contributing personal protective equipment throughout the crisis. One of the recommendations to leave you with is to forge paths for communication between regulators and creators and make publicly funded hardware available to supercharge response to the next crisis. On this series, open hardware can connect the dots between innovation and classic values of science, such as attribution through citation and quality assurance through repeatability and replicability. This set of authors also left us with recommendations for how to broaden ideas of inclusivity, such as with thoughts on where and how open hardware for science and the resulting data can be useful. And a recommendation to highlight is to prioritize multi-sector dialogue that recognizes different types of data to allow for the inclusion of new voices and forms of participation. The next slide, contributors to these articles look to understand the economic utility of working with open hardware, arguing for the value of distributed manufacturing and generating new jobs and supporting industry growth by cutting manufacturing costs and innovating more efficiently. In their articles, they discuss the importance of funding open hardware for science as leading to a higher return on investment because open tools can be used and built upon by other scientists, making the process cheaper and providing plenty of room for flexibility and customization. And a recommendation from this slide is to divert funding of proprietary scientific tool R&D in favor of open hardware. Government should strategically invest in open source R&D for the most important research tools in the country. And next, this group of authors talked about the value of reproducibility, both in research institutions and in other environments. And this emerged in the series as a key theme across many of the articles, and even brought up in the panel just before. More experiments are repeatable thanks to accessible methods and instruments. Open hardware tools are exposed to greater public scrutiny, which can improve the quality and reproducibility of data. And the collaborative economy of open hardware provides greater support for reuse and repurposing instruments in new types of experiments. Creating better reproducibility for scientific data requires a cyclical focus on considering data in relation to the hardware that's producing it. And a recommendation to leave you with is to support and protect frameworks that facilitate consensual data sharing between different open hardware projects to build data as a commons. In the next slide, this series of authors looked beyond tools for research to see the value of open hardware as actual infrastructure and as infrastructure building blocks that should provide the foundation for researchers and practitioners to solve complex societal problems. For instance, CERN is a facility that relies on open hardware as infrastructure through the White Rabbit project, ensuring the CERN network keeps time to the nearest nanosecond. And open hardware is even used as a radiation-resistant power supply for the emergency lighting in CERN tunnels. And a recommendation from this grouping is to prioritize open hardware as a way to create, standardize, document, share, and repair critical infrastructures. And finally, as many authors in this series argue, there is no science without sharing. Regardless of whether we are creating large collaborative communities, generating research agendas, or building the infrastructure on which that research sits, open hardware for science can help us to prioritize impactful research. We also enable more local research and collaboration through the use of adaptive and modifiable technologies. And to leave you with the final recommendation, use open hardware to demonstrate the complex challenges we face can't be addressed with one dominant perspective. The open hardware practices of highly adapted and evolving designs that can materialize living dialogues between users, developers, and manufacturers of science tools should be prioritized. So with the GOSH goal in mind of open hardware being ubiquitously used across the sciences by 2025, a mere 4 years away, we have a lot to do. But interest has been steadily growing. Success using open hardware and demonstrations of its value are occurring more and more frequently. And if we can provide open hardware the policy attention that it needs right now, this is the moment where we can ensure the place of open hardware in a collaborative, societally connected, efficient, and productive scientific agenda. And on my final slide, I'm just going to leave you with some contact information, the links to all of the articles, a few other useful links, and just to mention as well that the Gathering for Open Science Hardware community, the GOSH community, is putting together a series of writing sprints in 2021 around topics such as developing guidance on open science hardware for technology transfer offices and guidance for research funders. And we'll be opening up submissions for proposals to smaller writing workshops. If you would like to propose one around research topics or literature reviews or developing further policy advice that's aimed at different audiences, we'll welcome your contributions over at the GOSH Forum. Thank you very much.
Thank you, Shannon. Those were some great recommendations. And thank you for agreeing to share your slides so people can dive in a bit more. We have about 1 minute and 40 seconds left. So given that you've put your contact information on that last slide, I'll let people reach out to you individually. And would just ask you really quickly, you went through so many recommendations, but given that we have a new administration and a lot of interest in open source hardware as well as low cost tools, what would be the one thing based on your over a decade experience working on the ground in this area that you would advise leadership and government to consider?
Sure. I mean, there's a lot. And I think all the recommendations the authors have made are really excellent, and also the recommendations of the panelists. From my perspective, I think that our trust in science is broken, and our trust in many of our governing systems is broken. And we have a real opportunity to try to figure out ways to forge new bonds between science and society. So, you know, thinking about how we broaden inclusivity, broaden participation, that's really at the top of my mind right now.
Thanks for sharing that closing thought. And thank you again for your slides. Thanks to Megan and Zach and Stinger for your contributions earlier. Huge thanks to the Wilson Center's incredible AV team who continue to allow us function during COVID. And then finally, thanks to everybody who joined us today, either tuning in real time or by watching the recording after. Building community during COVID-19 is hard, but we would love to hear from you at that stip@wilsoncenter.org email address and learn more about what's happening in open science and open hardware these days. So thanks very much again to everybody and enjoy the rest of your evening.